I'm going to be speaking about a couple of items in two of our books, and if you go to reasons.org/Ross, we're giving away chapter 15 for free. And then we're also giving away a free chapter in Improbable Planet, and I'm going to focus on one part of one chapter in Improbable Planet for today's message. What inspired both the Creator and the cosmos and Improbable Planet was this idea that fine-tuning is not just to make possible the existence of life, not just to make possible the existence of human beings. When we look at the fine-tuning design of the universe, the Earth's life, and all the way down to the biochemical level, it's all fine-tuned to make possible the redemption of billions of human beings. And if you read through the Bible, what you discover is the claim that God begins his works of redemption before he creates anything, implying that everything that God creates is for the purpose of redeeming a huge host of human beings from their sin and evil. In other words, all God's creation works are for the redemption of billions of humans. And so I document in these two books how literally every event in the history of the universe, Earth and Earth's life, and every component of the universe, Earth and Earth's life, fulfills a role in making possible the redemption of billions of human beings. And you say, where do you get the billions from? Well, Buzz, you used this passage last night. I'm going to copy it again. Revelation 7:9. Before me was a great multitude that no one could count, from every nation, tribe, people, and language. But rather than refocusing on the diversity that Fuzz folks focused on in the breakfast this morning, I'm going to talk about the number. In Greek mathematics, they had a number system that could count up into the hundreds of millions. And so in the first century Greek culture, when they talked about an uncountable number, that meant billions plus. And so I look at this passage as a promise that God has designed the universe, Earth, and Earth's life in such a way that an uncountable number, namely billions of human beings, are going to come into relationship with God where they'll be free for the rest of eternity from sin and evil, and yet they're going to see their free will enhanced to be able to receive and communicate love beyond anything we can imagine in this realm. And so the message I've titled for this afternoon, Habitability for Redemption. In other words, what is it about this earth that we live on, this universe in which we live on, that makes it possible for billions of human beings to come into a redemptive relationship with the Creator? Now, in Improbable Planet, I discuss several hundred things, features of the earth that needs to be fine-tuned in order for the redemption of billions of human beings to be possible. Because we're looking at just half an hour this afternoon, I'm only going to focus on 3 out of the several hundred. Namely, that for the redemption of billions of humans to be possible, we humans must be living at a time when there's ice on the planet, and not just any kind of ice. We have to be living in a regular ice age cycle. And we have to be living at a time when the sun is exactly middle age, exactly halfway through its burning phase. And we have to be living at a time of extreme climate stability. How many of you have heard of global warming or climate stability, instability? Okay, I mean, all of you, right? That's kind of the big issue politically today. What a lot of our politicians and scientists are not taking into account is that climate instability is the norm. The climate stability we've had for the past 9,000 years is the extreme exception. We've been blessed with this brief period of a few millennia of extreme climate stability. And it's because of the current episode we're in the Ice Age cycle. Now, for most of Earth's history, there's been no ice on our planet at all. And when it's had ice, the ice sticks around for millions of years. What's unique about our time, the last 2.5 million years, is that we're in an Ice Age cycle where there's always some ice on the planet, but it varies between 10% and a little bit more than 20%. Now, the continent that's been impacted most by the Ice Age cycle is North America. Okay, so this shows you the amount of ice coverage on North America today. It's a little bit less than 10% of the total land coverage. But if we go back 26,000 years, 55% of North America was covered by more than 1,000 feet thickness of ice. And incidentally, in the wintertime, the ice would get all the way down to St. Louis. It actually, San Diego Harbor would be completely frozen over during the winter back 26,000 years. And then it kind of flips back to this. So it goes from 10% coverage to about 22% coverage. This shows you the Ice Age cycle. It's very repeatable. Every 100,000 years, we have an interglacial, where we only have 10% ice. Then for about 90,000 years, we have more than 20% of our planet covered with ice. But it'd be impossible for you to be here today, or for you to have the kind of technology that you enjoy today, or for more than a few million humans to be able to live on planet Earth if it were not for the fact that we're living during an Ice Age cycle. The reason we can produce the food to feed billions of human beings is because we're living in an Ice Age cycle. Now, I'm only going to take the time to discuss two benefits of the Ice Age cycle, but one that I think is obvious, especially for you living here in St. Louis, is melting glaciers water the soil-rich plains. I mean, the Missouri River is not far from here, right? The headwaters of the Missouri River are the glaciers in the Canadian Rockies. So all that water that's coming down the Missouri, it's basically water that's coming from the melting of glaciers left over from the last ice age. And this is a phenomenon that takes place all over the world. The great rivers of the world are all fed by glaciers and ice fields that are left over from the last ice age. So this map of the Northern Hemisphere, for example, that turquoise shows you those regions of the world that were covered by more than 1,000 feet thickness of ice 26,000 years ago. Now, as that ice melts, it feeds the great rivers that water the great agricultural plains. So, for example, you look at the food that is produced in India and China. It feeds 3 billion people, Southeast Asia, and they get their water from the melting of glaciers left over from the last ice age in the Tibetan Plateau. Now, that ice will eventually completely melt. But thankfully, the Ice Age cycle is about 100,000 years. So it means that, hey, before all that ice melts away, we get a restoration of that ice. But it's the melting of water left over from the last ice age that allows us to irrigate the great agricultural plains. And right here in the St. Louis area, you can see where you're benefiting from that meltwater to be able to produce a huge amount of food here in the Midwest. But here's another benefit. As the ice begins to rapidly melt, and that's one of the things we see in our Ice Age cycle, is that you get just 26,000 years ago, all of Canada was covered by 3,000 feet of ice. Within about 1,500 years, almost all that ice melts. And the rapid melting of ice with each Ice Age cycle causes a powerful wind to blow off the plateaus where the ice has been melted, and that causes this nutrient-rich dust to be deposited on the low agricultural plains, which means every 100,000 years, the Great Plains of North America, South America, Europe, and Asia get refertilized with this nutrient-rich dust. And it's a combination of that nutrient-rich dust and the water melting from glaciers left over from the last ice age that enables us to grow this huge abundance of food and enable billions of us to survive here. But not just a great abundance of food, but we're able to produce that food with 1% of the human population. Today, 7.5 billion of us live here on planet Earth, but the food is largely produced by just 1%. That explains why we have such great technological advance. If only 1% of the human population is involved in producing the food to feed everybody, that means the other 99% of us can be doing engineering and science and technology, computer science, medicine, and therefore we can enjoy this incredible technological advance that Fuzz was speaking about. And again, if you want to read more about this, there's actually a dozen different ways we benefit from living during an ice age cycle. And if you want to read about the other 10, again, get that chapter that we're offering for free from Improbable Planet. So that's one requirement. We have to be living in an ice age cycle. A second requirement is that we have to be living at a time when the sun is perfectly middle-aged. Now, the sun can burn through nuclear fusion, fusing hydrogen into helium for 9 billion years. And right now, we're exactly halfway through that burning period. But stars are a lot like human beings. They're unstable when they're young, they're unstable when they're old. They're maximally stable when they're middle-aged. But here's the difference. For human beings, our period of stability lasts 40 or 50 years. For stars, that lasts just thousands of years. There's only a tiny window of time when you get the necessary luminosity stability. So for example, this shows you the flaring history of our sun. Now, there are stars that are bigger than the sun and stars that are smaller than the sun. But both the stars that are bigger and smaller have greater flaring activity than the sun. The sun has the minimum. But with the sun, we discover that when it is young, the flaring activity is 1,000,000 times higher than it is today. That vertical scale is logarithmic. And so what you see is we happen to be living at that one time in the history of the sun when the flaring activity is minimal, and likewise that marks a time when the ultraviolet and X-ray radiation from the sun is at a minimum. Now, life has been here for a long time. If you're a bacterium, you can handle lots of solar radiation. If you're a human being, you can't. And so it explains why when we look at the history of life, we notice that for the first 3 billion years, it's nothing but microbes. There's a good reason. The physics of the sun only allows life of that complexity nature to exist. You literally have to wait until the sun becomes less active in its flaring activity. What we notice is the flaring minimum occurs when the sun is 4.57 billion years old, which is the age that it is right now. And it's through the study of looking at neutrinos coming out of the nuclear furnace a few years ago that we astronomers were able to determine that the sun entered an exceptionally stable luminosity phase in its burning a little less than 50,000 years ago. And it's going to exit from that phase in a little less than 50,000 years from now. And right now, we're exactly in the middle of that 90,000 year window when the sun has that maximum luminosity stability. However, I just mentioned that, okay, we need the sun to be perfectly middle-aged. We also need to be living at a time when there's ice on planet Earth and when we have an ice age cycle. And you heard me say that for 90% of Earth's history, we've had no ice at all. And yet we look at the luminosity of the sun with respect to time, we notice it changes like this. And so what you see is that through the history of life on planet Earth, the sun has been getting progressively brighter and brighter, which causes a paradox. I already said the Earth had, for 90% of its history, had no ice at all. You would expect when the sun is dim, you're going to get lots of ice, and when it's bright, you're not going to get any. But we see the opposite. Now, there's a reason. When the sun was that dim, we had lots of carbon dioxide and methane in the atmosphere. And throughout the history of life, we see that the carbon dioxide and methane goes down. And that really explains why the fossil record looks the way it does. God, knowing what's going to be happening with the sun, that it's going to be getting brighter and brighter, makes sure that we have life on planet Earth when we're talking 3.8 billion years ago, that actually pumps carbon dioxide and methane into the atmosphere, and as time goes on, that goes down, and eventually the light begins to remove carbon dioxide and methane from the atmosphere. But we have exactly the right life at exactly the right time and just the right abundance and diversity to ensure we get exactly the right amount of greenhouse gases in the atmosphere to perfectly compensate for the brightening of the sun. Now, having said all that, we still have an enigma. The sun is brighter than it's ever been before in the history of life, and yet we got ice. And how can we have that ice? And part of the problem is, well, maybe we could bring down the carbon dioxide some more. But what happened during the last ice age is the carbon dioxide level dropped so low it almost put a permanent end to photosynthesis. Right now we have in the atmosphere the minimum amount of greenhouse gases to sustain photosynthetic life at a high abundance level. There must be some other way we can cool the planet other than by drawing greenhouse gases of the atmosphere. And this is something that geophysicists have discovered just in the past few years, that there was a set of 5 simultaneous, unprecedented tectonic events that allowed our planet to be cool enough to have an ice age cycle in spite of the fact that the sun is as bright as it is, and in spite of the fact we needed a minimum amount of carbon dioxide to be able to produce the food crops that we do. So in the next few minutes, I'm going to review for you these 5 simultaneous tectonic events and how we need all 5 happening simultaneously in order to cool the planet sufficiently to get an ice age cycle. Okay, the first of these is what happened to Antarctica. Antarctica was attached to Australia some 70 million years ago. It broke off from Australia, but remained attached to South America. And about 20 million years ago, it broke off from South America and began to move towards the South Pole. So it moved towards the South Pole and then stopped when it hit the South Pole. As you look at Antarctica, you notice it's perfectly situated right over the South Pole. And that's going to help it to cool down. But the other thing you notice is how isolated Antarctica is from the other continents. It is the most isolated continent on planet Earth today. There's a wide swath of ocean water all around Antarctica, and that wide swath of ocean water set up a powerful current running around Antarctica and powerful winds. If you read any of the sailing novels of the 19th century, they talked about the roaring 40s. That refers to 40 degrees to 50 degrees south latitude, where you got these 40-mile-an-hour winds constantly blowing. Well, it's that powerful ocean current and those powerful winds and the location of Antarctica over the South Pole that cooled it enough that ice began to form. The ice we see in Antarctica is less than 3 million years old. It's only been there in the last recent history of the Earth. But it's such today that we got 1,000 feet plus of ice covering almost all of Antarctica. And ice has the property that it reflects sunlight very efficiently. So for example, open ground will reflect sunlight between about 5 and 10%, ice 50 to 70%. And so the reflection of sunlight away from the Earth actually has worked not only to cool down Antarctica, but literally the rest of planet Earth. That's event number 1. And this represents the largest coverage of ice on planet Earth today. But the second largest is what we see happening in North America. Greenland at one time was situated just off of Newfoundland. And then there was a tectonic event that caused Greenland to rapidly move up towards the North Pole, where today the northernmost landmass is the northern tip of Greenland. And what was interesting is not only did it move up there and stop at that northern location, when it stopped right over what we call a hot plume. A hot plume is something similar to what's taking place in Hawaii, where you got this plume of intermantle material rushing up towards the surface and forming the Hawaiian Islands. The state of Hawaii is the fastest growing state in the Union in terms of land area because of that hot plume. Well, Greenland moved over a hot plume. And what happened was Greenland, which used to have a very low average elevation of less than 500 feet, being under this hot plume, it wound up having an average elevation of over 8,000 feet. And because of its northern location and that high elevation, ice formed over all of Greenland. And again, ice reflects sunlight more efficiently than ground, and that worked to cool the planet. But the other thing the movement of Greenland did was to close in the Arctic Ocean. If you look at the northern hemisphere, just looking down on the North Pole, you see that the North Pole is surrounded, the Arctic Ocean is surrounded by these big land masses. Land masses are always cooler than open ocean. And so this actually worked to cool the Arctic Ocean and allow the Arctic ice cap to form. Again, a very recent event. Only in the last couple of million years has there been an Arctic ice cap. And open ocean water reflects sunlight at a 6% rate. Ice reflects it at 50 to 70%. So it's had a dramatic effect in cooling down planet Earth, the formation of the Arctic ice cap. And then event number 4 is what happened to North and South America. Now, with that powerful ocean circuit going around Antarctica, it caused the flow of cold water to move up from Antarctica all the way through the Atlantic Ocean. And so it had a cooling effect on all the land masses adjoining the Atlantic Ocean. But 3 million years ago, that was blunted by the fact that there was a water gap between North America and South America. And so warm equatorial Pacific Ocean water could flow between North America and South America and warm up all that cold water that was welling up from Antarctica. But beginning about 3 million years ago, North and South America began to come together and form the Isthmus of Panama. And what that did is it blocked the flow of warm Pacific Ocean water into the Atlantic and dramatically cooled all the land masses joining the North and South Atlantic Oceans. But the 5th event is the most dramatic of all. It's what happened to the 8th continent. I mean, you learned in school that there were 7 continents. Well, if you go back about 10 million years, there were actually 8 continents. There was the Indian subcontinent plus the other 7 continents. And the Indian subcontinent, 70 million years ago, was attached to the island of Madagascar. It broke off from Madagascar and then headed towards Asia. But it headed towards Asia at the phenomenal velocity of 22 centimeters per year. And you say, gee, that's not very fast. However, in geophysics, a really rapid tectonic plate movement is 2 centimeters per year. This is 11 times faster than we consider to be a really rapid movement. I mean, to help you visualize this, this is a typical rapid tectonic plate movement scaled down. It'd be as if I was walking kind of like this, okay? That's 2 centimeters per year, which is considered to be super fast. Compare that to 22 centimeters per year is where I'd be running across the stage. Consequently, when the Indian subcontinent finally reached Asia, it caused the seafloor between the Indian subcontinent and the Asian continent to buckle up. And those are the Himalayas. There's a reason why you find seashells at the top of the highest mountains in the Himalayas, because the entire Himalayan range is buckled up seafloor that resulted from the collision between India and the Indian subcontinent and Asia. Incidentally, that collision is still proceeding. If you were to ask me, what's the second fastest plate tectonic movement in the history of the Earth? It's what's happening with the Indian subcontinent today. It's moving at 5 centimeters per year northward into the Asian plate. And so the Himalayas are getting taller and taller every year. Sir Edmund Hillary did not climb the world's highest mountain. Mount Everest is 1.5 feet higher today than it was when Sir Edmund Hillary climbed it, thanks to the fact that this collision is ongoing. But this collision also caused the Tibetan Plateau behind the Himalayas to continue rising up. 1 million square miles of the Tibetan Plateau now has an elevation of 17,000 feet above sea level. That's the average elevation. And even though it's so close to the equator, because the Himalayas are so high and the Tibetan Plateau is so high, ice is formed over the Himalayas and the Tibetan Plateau. It is such that the 3rd largest store of ice on planet Earth is not the Arctic ice cap. The 3rd largest store of ice is the Tibetan Plateau and the Himalayas. And I mentioned earlier that it's the melting of water left over from the last ice age. It's the melting of ice over the Tibetan Plateau that is feeding the Ganges River, the Yangtze River. I mean, all the great rivers, 22 huge rivers flow out of the Tibetan Plateau into Southeast Asia, China, and India, and that's what enables more than 3 billion people there to be able to live. It also explains why each ice age in the ice age cycle is more severe than the previous one. Why? Because the Tibetan Plateau is still going up. And so the last ice age, we had 23% of our planet covered with ice. Canada and Siberia were covered with 3,000 feet thickness of ice. And also because of the rising of the Tibetan Plateau, when the planet warms up, you get a very rapid melting of that ice, and that results in the formation of fjords. The fjords of Norway were all cut just thousands of years ago by the retreating of ice. If you ever visit California, Yosemite Valley was cut by the retreat of ice just thousands of years ago. There are other benefits as well. But in order for billions of humans to live on planet Earth at one time, it's critical that all 5 of these unprecedented tectonic events happen simultaneously. Take one out of the equation and you get no ice. You need all 5, and all 5 must happen simultaneously in order for this ice age cycle to occur. Now, I wrote an improbable planet. What drives this ice age cycle are subtle changes in the orbit of the Earth. So, for example, as our planet orbits around the center of the sun, the shape of the orbit changes. When it becomes more elliptical, that warms the planet. When it becomes less elliptical, it cools the planet. And likewise, the tilt of our rotation axis changes between about 22 and 24 degrees. And when it goes up to 24 degrees, that warms the planet. When it drops to 22 degrees, that cools the planet. Now, the eccentricity is a 100,000-year cycle. The tilt of the rotation axis has a 41,000-year cycle. And we also have discovered, literally just in the past couple of months, I'm writing an article on it right now. It's going to be appearing on October 4th as one of my blogs, making the point that we've discovered another factor that's driving this cycle. It's the fact that every 100,000 years, Earth passes through a dust cloud of meteoritic dust in our solar system. And whenever we go through that dust cloud, it cools the planet down. Bottom line is, we've now identified 9 different periodic cycles that are responsible for driving this ice age cycle. But because there's 9 different cycles with 9 different periods, it leads to great climate instability. So this shows you the last 4 cycles of the ice age, and you can see that the temperature jumps up and down throughout the ice age. And here's a detailed look of the previous ice age, when we had 20 to 23% of the planet covered with ice. And what you notice is that the temperature, global mean temperature, during the last ice age was jumping up and down by 24 degrees Fahrenheit on time scales of 1 or 2 centuries. It explains why humans that were living here 35,000 years ago were developing technology. But the technology was on a very small scale. And we have recent evidence, for example, that humans at that time were building hearths, they were harvesting grains, they were grinding the grains, they were roasting the grains, and using it to make bakery products. Incredible technology, given what they had available at that time, but was all on a very small scale, which explains why it wasn't discovered until the last couple of years. But the reason it had to be small scale, they didn't have the climate stability to be able to scale up, where you could actually have people specializing in doing this in a very large scale. That requires extreme climate stability, and that did not exist during the last ice age. But for the first time in the ice age cycle, beginning 9,000 years ago, these 9+ different cycles all came into sync to give us a short period of extreme climate stability. Over the last 9,000 years, the global mean temperature has not varied by more than 2 degrees. And because of that extreme climate stability, and because the global mean temperature was at the optimal level for human civilization, we've been able to go from a few million human beings to billions of human beings, from very limited technology to having very high technology, where the technology is literally exploding year by year by year. Because during the last ice age, 99% of the human population had to be dedicated to producing enough food for everybody to eat. Today, just 1%. And because it's just 1%, we've been able to sustain a huge population at a very high technology level. Now, I've presented this message before audiences of scientists who are not theists. And their response to all this is, well, Hugh, we just think this is all a bunch of sheer coincidences. My response to that is, yeah, but they're simultaneous coincidences. And this is just one example. I only showed you 3. If you had enough time, I could show you dozens of more, but I'll end with just this one little insight. This 9,000-year period of extreme climate stability, where all these things come into sync simultaneously, also coincides with a period when we've had no nearby supernova eruptions. Our Milky Way galaxy has 3 supernova eruptions per century on the average. And the only period in the history of the Earth where we've had no supernova closer to us than 5,000 light years has been the last 10,000 years. It never has happened before. And because we've had no supernova closer to us than 5,000 light years, there's been no limitation on our food production. Whereas during the last ice age, they had multiple supernova events that were closer to us than 1,000 light years. And when you get supernova that close, it won't kill human beings, but will sure do a lot of damage to the crops that we depend upon for food. But that's not happened in the last 9,000 years. And therefore, that's another reason we've been able to develop the food that we need to feed so many of us and to do it so efficiently. Again, the text, Revelation 7:9. Before me was a great multitude that no one could count, from every nation, tribe, people, and language, that will be standing before God, worshiping Him, completely free of sin and evil, and set free to experience love at a level that is utterly unimaginable for those of us living today. That's only possible because of the incredible fine-tuning design that God has built into the universe, Earth, and Earth's life over the past 14 billion year history of the universe and 4.5 billion year history of the Earth. My colleagues who are not believers look at the fine-tuning argument and they basically don't see the whole picture. By putting it in a redemptive context, you really get an overwhelming argument that this is all fine-tuned repeatedly, continuously by a creator intent on redeeming billions of us from our propensity to do evil.